In order to consider what happens with the compound interest formula, as the number of compounding periods n increases, we're going to look at a bare bones version of this in which the rate is 100% and the time is 1 year. Just to get these numbers out of the way, and also that our principal is $1. Just to get these other letters out of the way and get down to something that has only ones and ends. It makes sense that if we compound our money more times in a year, it will grow faster, right? We would expect that to generally be the case. It also makes sense that we might see a diminishing return. Changing our compounding from once a year to twice a year probably makes more of a difference than changing it from once a day to twice a day, right? So we're going to look at this expression here. 1 plus 1 over n to the power n, and let n increase. So the number of compoundings per year is increasing. Just looking at n equals 1, we could see that a would be equal to 1 plus 1 over 1 to the 1. So very quickly we see that that's 2 to the power 1, which is simply 2, right? If we were to look at n equals 10, we would get a equals 1 plus 1/10 to the power 10, which is the same thing as 1.1 to the power 10. And I can bring in a calculator to evaluate that and confirm 1.1 to the power 10 does get us this 2.5937, etc. So the rest of this table has been filled in for us. But what we can see here is that by the time we get up to n equals 100,000, our A is not changing in the first 3 digits past the decimal point. That the change is moving further and further out in this expression. And in fact, this does converge on a number. This converges to a value that we call E. And the approximation that we most often use of E is 2.718. We've already seen this sequence converge to that many digits. Of course, this is an irrational number, so we could keep going forever and we would still not have exactly defined E, but we can get decimal approximations of E. You can find E on your calculator. Most calculators have an E to the X button. This one just has an E button. So if I just hit E, I can see that it comes up 2.718. I can see the next digit is a 2, so it looks like that one was also correct at n equals 100,000. If I want to raise that to a power, on this calculator I would use E, and then I would use my power button. So E squared, for example, is going to get me 7.389. Most calculators have an E to the X button so that you don't end up having to do a combination of buttons to do that. If I want to now approximate to 3 decimal places E to the 1.8, I'm going to take my E button, then hit my power button, and then enter 1.8. But the exact sequence might be different on your calculator. Try it out and verify that you can get 6.049, 647, etc., that you have the right keystroke sequence for your particular calculator. So I'm going to round this off to 3 decimal places, which is going to be 6.050, since I have to round up from 6.049. So now that we've established that as the number of compounding periods increases, it looks like the compound interest formula seems to converge. We are ready for this idea of interest compounded continuously. Compounded continuously means that no actual time passes in between compoundings. And so we have a new formula for this, and not surprisingly, it uses that E. Our formula is A equals P times E to the RT. So we know to use this formula as soon as we see compounded continuously somewhere in the instructions of the question we're being asked. So let's identify what some of the other values are. If $100,000 is the amount in your account after 18 years, that's not the principal, that's the amount A. Sometimes you're given the principal, sometimes you're given the amount. That could happen on any compound interest question, whether it's continuously or another kind of compounding. My rate converted to a decimal is going to be 0.1025. And also I'm given a value of t. That 18 years tells me that t is equal to 18. And I want to know how much money I need to invest now, which is my clue, my further clue, that P is actually the unknown this time. So plugging all of these in, I get that A is equal to 100,000. P is the one I'm going to leave as a variable. E is a constant, so E stays the same. R is 0.1025, and T is 18. I'm going to solve this symbolically for P. All I have to do is divide both sides by this whole power of E. I'm going to leave everything symbolic so that I can get the calculator to do everything at once. It's that rounding error thing again. If I round off 0.1025 times 18, I'm probably going to have some rounding error that would cause problems. So that the expression I want to let my calculator handle is 100,000 divided by e to the 0.1025 times 18. And I am going to have to make sure that I put this product in parentheses so that my calculator treats the whole thing as an exponent. Here's how I'm going to do that on my calculator. 100,000 divided by e to the power, open parenthesis, 0.1025 times 18, close parenthesis, equals. And I get 15,802.53. Now I'm just going to look at this and make sure it seems reasonable. We're talking about a period of 18 years, this amount of money, $15,000 roughly, 16,000 maybe, growing to 100,000. That might sound a little optimistic, but we are getting a 10% interest rate. It does seem ballpark, at least reasonable. Right? If we had gone in the other direction and plugged in for P instead of A, we should get something that is nowhere near close, right? So it's always good to look at your numbers at the end and see if they seem somewhat reasonable for the question.